This problem is a bit different than the others. We're given a power supply, in this case 13.8 volts DC, and we're given an RC circuit such that when the switch closes, the capacitor, which is initially uncharged, will charge. But it's different because this time we are asked at what time, again, at what time does the voltage on the capacitor equal to 10 volts? It's useful to look at the note card for our RC transient circuits for a situation where we have an initially uncharged capacitor. We see this behavior as a function of time. The voltage on the capacitor increases. In fact, it follows this curve right here. And as time reaches infinity, the capacitor will be charged to the source voltage. That curve is described by this equation where we see that the voltage on the capacitor as a function of time is equal to the source voltage multiplied by 1 minus e to the negative t over tau, where tau is equal to the product of R and C. In this particular problem, we are given that the voltage on the capacitor is 10 volts, and we're asked to find time. Before we start, it's also useful to review some of the rules for the natural logarithms and e, in particular, the inverse functions. Now stay with me for a moment. We have two functions. We have f of x, which is equal to e raised to the x. We also have g of x, which is equal to the logarithm of x. Now, if we take f of g of x, that's the same as saying e raised to the logarithm of x. When we do that, we get x. Likewise, when we take g of f of x, that's the same as saying the logarithm of e to the x, which is equal to x. Now remember these as we go through this particular problem, especially this property right here, as we'll need it. We reach a point where we need to solve for this x, and basically we need to break it out of jail. And one way to break the x out of jail is to take the logarithm. Now, back to our original circuit, and the first step is to solve for tau. So tau is equal to the product of RC, which is equal to 1,000 ohms multiplied by 10 microfarads. And if we solve for that, we find out that tau is equal to 10 milliseconds. From there, we need to set up our equation right from our note card. Again, solving for voltage of the capacitor as 10 volts. So 10 is equal to 13.8 multiplied by 1 minus e to the negative t over 10 milliseconds. If we continue on, we divide both sides by 13.8, and then we subtract 1, and on the right, we're left with negative e raised to the negative t over 10 milliseconds. If we go a little bit further, we end with 19 over 69 is equal to e to the negative t over 10 milliseconds. By the way, that's one of the reasons I like this calculator so much, is that it gives us the fractions directly. For instance, if we go 10 divided by 13.8, and then if we were to subtract 1 from that, you can see that it gives us the fractions directly. All right, so again, taking care of signs here, this is what we're left with. Now, back to our note card, you recall this property right here, where we wanted to take, or if we want to get x out of jail, we take the natural logarithm of that. So the natural logarithm of e raised to the x gives us x. So if we come down here, if we were to take the natural logarithm of e raised to the negative t over 10 milliseconds, we would get negative t over 10 milliseconds. So doing that, we take the natural logarithm of 19 over 69 and the natural logarithm of the other side of e raised to the negative t over 10 milliseconds. And so we take back to our calculator, natural log of 19 divided by 69 gives us negative 1.29 is equal to negative t over 10 milliseconds. And solving for t, we get 13 milliseconds. It's useful to check our results real quick using the calculator. So we'll take 13.8 multiplied by 1 minus e raised to negative 13 divided by 10. And we close, gives us 10 volts, which is exactly what we started with in the original problem, 10 volts.